In the name of Allah, the Compassionate and the Merciful. Hello guys. My name is Salar Delavar Ashghai, and in this video we're going to talk about the Ductility Damage Index, this seismic performance assignment of Gable frame. So you see that guys, in this picture we have one Gable frame with 4 non-prismatic elements and with 200 nodes and 600 degree of freedom. And for this Gable frame we used 196 prismatic elements for simulating these 4 non-prismatic elements. And the section is a structural properties is the symmetric, and we use linear relations between section 1 and section 2 and section 3 to section 4 properties. And for calculating the structural damage index, we must run 2 kind of analysis. The first one is a nonlinear static analysis, which is called pushover analysis, and the second analysis is nonlinear dynamic analysis. So in pushover analysis, we want to run and calculate the yield displacement and ultimate displacement. And in nonlinear dynamic analysis, we want to calculate the demand displacement during the maximum absolute value of, for example, outputted displacement from node 150. And we have actually 4 types of ductility damage index. If you want to indicate the damage for your truss element, you can use this formula. And if you want to indicate the sectional damage index, you can indicate this formula with the calculating the curvature of each sections. And if you want to indicate the element ductility damage index, for example, you want to calculate the damage index of this element, so you can use this formula. And you see that guys, if you wanna calculate the all structures damage index, you can use this formula. So in this process of calculating of damage index, we want to use this formula. So first of all, we run the pushover analysis to calculate the delta y and delta u as the ultimate displacement and yield displacement. And based on nonlinear dynamic analysis, we are going to calculate the demand displacement as a maximum absolute value of displacement time history, which is called PGD. And so in this video we are going to run these 2 kind of analysis to find the optimum section 2 web height. So in here we are going to evaluate this section web height. And you see that guys, after 78 iterations we get the solutions, and it gets so much time. I think it takes about 3 hours for this calculation, and your computer must have a very good power to run and get the result. And you see that, guys, let's back to the Opensees file. You see that, guys, I defined many functions to running and calculating some parameters. In here I defined many functions to calculating and plotting data, and in Pushover I defined Pushover analysis function for this Gable frame calculations, and also in here we're going to output the displacement of node 150 and base shear of node 1 and node 200. And then we have the same process for this nonlinear dynamic analysis. You see that, guys, all the section and element properties is the same, and in here we're going to output it with displacement and base shear of each nodes for displacement 150 and base shear number 1 and 200. So and in here we're going to have an optimization problem. So column length, beam length, and beam height, this element is going to be calculated. And you see that, guys, I defined section properties for beam and columns. So it's column properties and it's beam properties. So I defined this structure as nodes for 200, and I want to apply the incremental displacement in node 150 with the uniform distributed load -10, and then in here I want to find the optimum section web height of this section, as I told you before, and I used Newton-Raphson method for this calculation. And in this process I don't want to find optimum sections for this valuation. I want to calculate the negative demanded ductility damage index. So the negative value is not the damage index, it is the safety index. Okay, guys, so I want to use the structures to be safe during the seismic, and I use the negative value for this calculation. So you can use, for example, use 10% ductility damage index and find the optimum sections. Okay, guys, and I use the negative value, so I want 40% safety for these structures during the earthquake. And if I run this code at the first pushover analysis, then dynamic analysis, then waiting for some seconds for reading the outputted data, and then calculating the bilinear curve fitted, and then calculating the ductility damage index. So in here, when we run the pushover analysis, we have curve like this, and you see that, guys, the blue line is the real analysis outputted data, and then the red one is a bilinear fitted of this analysis. So in this red one, we are going to calculate the structural stiffness plus plastic stiffness as a slope of this value, and then structural tangent stiffness. It means that the slope of this line, and then overstrain factors, ratios between this and this value, and then ductility ratios between this and this value. And then during the nonlinear dynamic analysis, we're going to find the PGD as a maximum absolute value of displacement in node 150. So based on two kind of nonlinear analysis, we calculate the yield displacement, ultimate displacement, and demand displacement. So you see that, guys, based on this structural damage index formula, we're going to calculate these values. So if you see that if we run the nonlinear dynamic analysis, so we have two kind of outputted data, such as displacement, time history, and base shear history. So we use the absolute values to plotting the pink line. See that, guys, in here? Pink line. And so all analysis data is going to be run and then outputted and then calculate the structural damage index. And in here, after calculating the ductility damage index, we want to evaluate the outputted damage index with the target damage index. So our target damage index is minus 0.4. So after running the code, you see that after 87 iterations, we get the solutions with this convergence residual, and it is very good for this convergence. And it takes so much time. Your computer CPU must have very good efficiency for running this kind of analysis. So, but you see that, guys, most of the time you have a converge problem and you don't know the exact value for optimum evaluation of finding the best web height section from bottom and or top of this column. So I recommend you use the sensitivity analysis. So we do the same process with the sensitivity analysis, and you see that, guys, all the properties is the same, and we indicate the 200 iterations with various uniform column web section height and beam section height. You see that, guys? I use the uniform distributed function. So for example, for column minimum value is 280 and maximum value is 350. And also for beam section web height, start from minimum 80 and the maximum value for beam web height is 150 as a uniform distribution function as a random numbers. You see that, guys? And this kind of analysis for just 200 iterations, it takes about 9 hours. So it takes so much time for these calculations, and we based on this analysis, we're going to calculate the structural ductility damage index. You can change your process, for example, for calculating the elements damage index or section damage index. Okay, guys? If you want to calculate the For example, section damage index, you must find the curvature of each section during the pushover analysis and dynamic analysis. And let's back to the result, and you see that ductility damage index for this 200 iterations, it has this shape, and pushover displacement, base shear, distributions functions, and displacement after dynamic analysis as a delta D, I mean this value, and other parameters such as ductility ratio as this shape, and overstrain factor, it has this shape. And also you see that, guys, maximum absolute base shear, it has this shape, and you see that, guys, the maximum values in here and in here with the most frequency. And let's see in here we're going to plot the two parameters and find the best fitted line. You see that, guys, all the parameters data R squared is very low, so not good fitted for these linear relations. We use the linear regression, and you see that, guys, all parameters is the same R squared, and if we use the multiply regression with the all outputted data such as displacement, column section web height, rim section web height, overstrain factors, ductility ratio, plastic and elastic structural stiffness, and pushover displacement, base moment, and dynamic displacement and base shear outputted data, and calculating the multiplier regression. You see that, guys, this value as a dynamic, for example, in here, dynamic maximum absolute value of base shear has more p-value, more than 5%. So in next process, we're going to omit this data and running the next multiply regression line to fitting the best multiply regression and to finding the optimum line for the relations between all outputted data. And in correlation data, we use the all outputted data. You see that, guys, in some values, for example, in elastic stiffness, plastic stiffness, elastic stiffness, and some other parameters, we have very high correlated. And if you wanna to find the relations between these values, you must work it on it and trying to omit some parameters and find the optimum relations between these values. So I used other analysis such as machine learning, long short-term memory as a LSTM method for calculating the relations between plastic structural stiffness and ductility damage index. You see that, guys, after 300 iterations it gets some results. So you see that, guys, this kind of analysis is very complex, and you must working on it to finding the optimum ways and running this analysis. And also this shows the valuation of structural outputted data during the analysis. And you see that, guys, in this video we run this Gable frame with pushover and dynamic analysis and then trying to output the structural ductility damage index and finding the optimum section web height for the optimization problem, and then using the sensitivity analysis with the definition of finding of various uniform data from this section and this section. I mean these values as a column top of the web section and the beginning of the web height of beam 1 section. And you see that, guys, running and checking the analysis is very complex, and based off the statistics method you can find your solution to calculating the best way of these optimizations and sensitivity analysis. These videos which I prepared is just for educational purpose. Please have a comment and tell me know about this kind of modeling. God bless you guys. Bye.